before I start, so I posted per request on Piazza the homeworks. I mean, it's not a lot of text, just like a few bullet points of things, if you have some free time that you can work on. I created a new channel, homework, so you can join it. So the thing you haven't seen yet for System F is how you can program in it, and it appears to be like a bit boring at first, right? So I mean, there's not a lot of stuff you can do, but as you'll see, you can encode a lot of types in System F. Almost all, almost all the types you've seen so far you can encode in System F. So let's maybe start with unit. So the unit type is what? So I claim looks like this. So how can you see that this is unit? I mean, first of all, it seems to be not very useful, right? I mean, so if you have this, well, maybe let's start. Let's maybe before we discuss it, say what is the unit itself. The only value of this. So, well, there's not so much we can do, right? So I mean, we have the for all, so we have to start with a type abstraction with a big lambda. So for all t, right? What is a
T is a type.
Syntax? Yeah. So, right, I use the syntax that Bob uses, and then, I mean, what do we have to do now? So we have to use a small lambda because we have the arrow. There's no other way. So we have to use the small lambda. Argument has to have type t. And then, I mean, what can we do? We have to return something of type t. X, and there's really no other way. I mean, what else could you possibly do? With all kind of like, intuitively, with every step, we didn't have an option. First we have to do the abstraction, right? Then we have to use the lambda. We have to use type t here, and then we have to return something. Of course, you could do something like, weird there to return something of type t, maybe feed something into the identity function again, so you can blow it up a bit. But up to isomorphisms, this is the only type, the only value of that type. So this is unit, and you can't do so much with it. So I mean, if you have this, well, what can you do? You can put something in, you get it out again. So it's not computationally very interesting. So what else would you like to have? Pairs. We said like, you know, pairs or products. It's something you want to have in your programming language, and now come, you know, Reynolds and Girard, and they don't even have. It's a bit embarrassing in System F, but so as you'll see, they are actually there. So tau 1 cross tau 2 is what? So it's for all R, and now it's always the same scheme that we use when we construct these types. So it always ends here with arrow R, and in the middle part we kind of like list as arguments of this function all the constructors basically. So if you want to so for the pair you only have one constructor that, you know, takes what, something of type tau 1 and something of type tau 2 and gives you this pair. So and this is what we fill in here. Does that look good? Yeah. So and then we have to say, okay, what is a pair? So pair E2. Okay, so that's always the same. I have to first do the type abstraction. So then I have lambda, right? So that takes in a function I don't really have an option there. And something of type R. So how do I do that? I mean, of course, I want to have like a pair of E1 and E2. So, and they, you know, that should be the pair tau 1 cross tau 2. So E1 should have type tau 1, E2 should have type tau 2. So I have those around, so what do I do? Well, I put them in here. E1 goes first, E2 goes second. That's it. And conveniently, that's also a value, so nothing, you know, goes on there. Yeah, question? This here? Yeah, so it's a bit difficult to explain, but the recipe to construct it is basically, well, you know, so, I mean, there are multiple ways of looking at it. So one way is to say like, okay, you always have this shape that at the end you get something, you know, of type R, and you list here in the middle all the constructors. So if you want to, you know, construct a pair, what do you do, right? So you have to have, you know, something, you give it something of type tau 1, and you give it something of type tau 2, and then you have a pair.
So inside the parentheses, that's a single constructor.
Yeah, right, this here basically.
Yeah, okay.
And if you had multiple, then you have like more arrows. So that's one way of looking at it. Another way of looking at it is like, well, so you want to perform like, you know, computation on a pair. So what do you do? So well, you know, some computation that takes a pair and, you know, computes something of type R. So, well, what I say is, well, you know, why don't you tell me what you want to do with these elements, right? And I'll tell you what the result is. So kind of like if you know, want to compute something with a pair, you just tell me what you want to compute with a first and second element, and that's kind of like, you know, the essence of a pair is kind of like this. So that's another way of looking at it. Yeah.
So the type parameter, right?
Yeah.
So why can't we have two type parameters for first element and second element?
Oh, because these are kind of like given to us. So you tell me, you know, describe me a pair of type, you know, tau 1 cross tau 2. And, you know, if you have given me different tau 1 and tau 2, you know, I give you different thing. It looks exactly like that, but it's kind of like given to me and I describe what a pair of tau 1, tau 2 is. Okay, so then we want to also know what the projections are. So E dot L is what? So E is now a pair, right? So what can I do with it? So it has like this for all type here. Yeah. So the only thing I can do is I can apply it to a type. I have to give it a type, right? And interestingly, the type that I give it is kind of like the thing I get at the end. And here, what do I want to get? When I want to get out the left element, what type should it have? Tau 1. Right, so why don't we do that and give it tau 1 here. So the next thing I have now to give it is a function that you know, takes something of tau 1 and something of type tau 2 and then returns something of type tau 1. So why don't we do that? So here we don't have a choice, right? So we have two arrows. So we have to have two lambdas. And now we want to return something of type tau 1. Well, what can we possibly do? I mean, give the x1. And conveniently, the whole thing has now type tau 1 because that's what we plugged in for the R. So that seems to be a great fit. So how about the other projection? What do we do now? Tau 2, exactly. And what function do we give it? Yeah.
Basically the same function except it returns x2 instead of x1.
Exactly. And so we give it the same function, but just return the x2, which magically has the right type now. Oh, Yeah, right. So I think Paul was just writing the application also with a round ones. I think. Yeah, it's just the application to type application. Yeah, yeah. Yeah, I usually write them as a square to distinguish them, but yeah, it's just a normal application. Say like, oh well, you know, so the elimination form here, the projections, this is basically all you can do with a pair. I mean, you basically, the only thing you can do with it, give it like one of these two functions to get out the first or second element. So in essence, that's all there's to do with a pair. So next up, the binary sums. So first, what is the type? Tau1 plus tau2. So, I mean, we always start with a for all R. That much is clear. And then we also always end with arrow R. So that's always how they look, these encodings. But what goes in the middle? So how many ways do we have to construct a sum? 2.
You need to do it twice because you do it once for the case where it's tau1, once for the case where it's tau2. So like you just bring out some other name like tau prime, which is either tau1 or tau2.
Not quite. We don't have to add another name.
But we use the case. So we use the case keyword.
Well, here we just write down the type. So here's not yet. Yeah, we're gonna come to the defining the case, but not quite yet. Yeah. Yeah, right, exactly. Tau1 arrow R. So that's one constructor, right? And then tau2 arrow R. And then we get R. Good. And then we have to say what are the injections, the constructors. So L dot E. So E is now something of type tau1, right? And we want to inject it into the sum. So that's where we add, and we want it to be like of this type that we've written there. So again, we just follow the type structure and we can't go wrong, basically. So we have to start with the abstraction, okay? And then we have a couple of lambdas, so there's no choice even. What can we do? So we have F1 and have F2. Okay, just copying it. And now we want to get something of type R. So what are we going to do? call F1. Exactly. Call F1 with E. Perfect. So it's not so clear what's happening, but it seems like that's the way it has to be. So, and it's correct.
What about F2?
What about F2?
What if you go to that? Oh, is it you just work 2?
Yeah, F2 will come to that now. So up there, we just don't use it. Yeah. So here, thing, don't really have a choice. Just have to follow this, and then this time the maybe it would be better to call this here E1 and the second one E2. So and this time we have to use the F2. Yeah.
All these types are in arrow form. Is it because system only has functions?
Right. Yeah. Yeah.
We're allowed to skip we're allowed to skip F1 when we do R.E2, we're like, we have a function, but we have a convention where the tau1 arrow R type is the first slot of, it takes an argument list.
Right.
But we're allowed to skip a slot in the argument list, and just it'll plug into the right slot.
No. There's nothing of that kind going on here. So we're not skipping any arguments. So everything has the right type, right? I mean, so yeah. So this thing here has like the type as it's written there, right? So I mean, it takes a first argument that is like function, takes a second argument that is a function, and then returns something of type R, and then we abstract the type, so we get something of type for all R. So there's no fancy business going on here, right? Nothing special needed. Okay, so then we want to do the case. So let's see if we're able to do that. Case E. Oh, wait. X1, E1, X2, E2. Okay, how does that work? So now we have our E here, which has this type, and the E1 and the E2, they should be of some return type tau. So let's just say so they should they have like also a context, blah blah blah. But I just say like they should both have like this return type tau. So what do we do? So at the end of the day, we want to end up with something of type tau, right? I mean, because the whole case expression has type tau. So, and we want to use, of course, the sum. So if you look at the sum, and at the sum type here, and you look at like these two arguments you give it here, that kind of like, reminds us a bit of this E1 and E2, right? These are the two branches of it that you have here. I mean, E1 takes something, of type tau 1, and E2 takes something of type tau 2. Yeah. So what we do, well, we just use E. We want to have something at the end of type tau, so we apply it using my square brackets again, but it's the same thing as like the other one. Okay, and then I have to give it, to get something of type tau, I have to give it two arguments now. And what will be the arguments? So first argument is this one. And the second argument is this one. So what will happen now? So if E happens to be the left injection, then we will run the code of the F1, which is basically the E1. If E happens to be the right injection, well, then we're going to run F2, which is basically E2. So it does exactly the right thing, what we wanted to do. Yeah, pretty cool. And yeah, it's even like here, I mean, it would be kind of hard to come up with like, a different definition to write here. So it kind of like all happens automatically, and it, it does the right thing. The only thing you have to do is to come up with this type, but if you do this constructor trick, it's, fairly mechanical even, to translate these. So last one I have is natural numbers. So there, what is the type? So again, we start with our trick like this. Yeah.
Do you have to recurse, like pull out of mu, because it's the, I mean, nat is a recursive type.
Right.
So
how many constructors does it have? Two. Okay. So that's one has like unit as an argument?
Yeah.
Okay. And the other one has an argument that is successor, but like what's the type? Nat arrow nat. But here the nat
Nat arrow R.
almost, so arrow R is always good. But we said it's nat arrow nat, right? So then here in this case it's R arrow R.
Oh, R arrow.
Right. And we can simplify it a little bit and can leave out the unit here. Doesn't add anything. If you have like function like unit to R, it's basically the same thing as R. It's isomorphic, we say. Okay, so let me clean that up a bit. Okay, that looks good. So now, what is 0? Okay, let's see. So, well, type abstraction. R. Well, not quite, right? Because it doesn't have the right type, right? It needs to have like a type with 2 arrows. So we have to further follow the type structure, right? So it has to first have something, well, let me just call it Z for whatever reason. And then it has another thing, let me just call it S for basically no reason. And then we want to return something of type R. So, yeah, we don't have an option really. So, and same thing. So, now what? And now it becomes a little bit weird. But so what you really want to do now is you want to say something like, yeah, so but we want something of type R. We of course want to use E somehow. So what we'll say is basically S of E, but that does not quite work because what's the type of E, right? E is a nut. That means it has this type. So and now it, yeah, that's why I say it becomes a little bit weird. So you have E. So you want to do somewhat S of E. So but E has the wrong type. So E is like this, you know, for all R. And how can we turn it into something of type R? Well, we have to apply it to something. So the first thing we can apply it to is, you know, some type. So if we want to have something of type R, our R here, which is different from the one up there, but anyway, so if you want to have something of type R in the end, better apply it to R here. So that's already a good idea. So then the next thing it takes is something of type R. Well, we only have one thing around, which is Z, and then it wants something of type R, arrow R. So, well, so That's it. So it looks a bit strange, but it's not so strange really. Because it embodies what you can do with a natural number. And what can you do with a natural number? Well, you can do recursion. And that's exactly what this does. So if you have like this natural number, what do you do when you want to kind of like use this, when you want to do a computation? You say, what is the type of the thing I want to compute? Whatever it is, maybe it's a list or whatever. Then you have to say what is like the base case. Maybe it's the empty list. Plug that in here. And then you have to say like, okay, if you go from n to n plus 1, what should happen with the list? What should happen with the thing you want to construct? And then what will go on here is if it's if the natural number you kind of like do the iteration on, if it happens to be 0, well, you just run the base case, which is maybe the empty list or something like that. And if it's not 0, well, what you do, you take the predecessor and you kind of like call it with the same thing, with the base case and with the iterator. This will, compute the result for the predecessor, and then you apply kind of like the iterator one more time to get the next thing. So that's how the natural numbers work. So, yeah, we had this cursor in one of the lectures of Paul. I'm not sure if it's the same thing. Don't remember. Oops. Yeah, where you have a natural number e, and then you have a base case e1, and then you say like, okay, how do you compute the next thing? And well, how do you do that? So that's the only way you can use a natural number. So you have to apply it to some type tau, but what I said is like the list, your end result you want to have. Then you give it the base case, and then you give it like the step function that is called iteratively. Takes in the result that you have for the predecessor and gives you the result for the current number. So, okay, so I have I could do a little bit more, but I don't want to keep you for longer. So the homework is, I posted already on Slack, is define lists of type tau in this way, where you then would define what is nil, what is cons, and what is like an iterator for lists. Okay, good. So everybody's tired now. Questions? Good. So then, that's the end of polymorphism. Tomorrow, linear logic by Paul, and I will leave. Okay.